Hi, Professor Wang.
Hello,
Hello,
Professor.
how are you?
I'm sorry. Yeah.
Yeah.
Nice to meet you.
Nice to meet you. Nice to meet you. I hope to see you here. Yeah.
I have been published 4 years ago, or more than 5 years ago.
You know, we have had email communication on several occasions before.
Yeah, at the beginning of this year.
Yeah, Mr. Zade applied to continue his studies in your group.
Yeah, it's a very pity he has not be passed the initial selection.
Yeah.
Even not to my hand.
Yeah.
The material at the very early stage.
Yeah. Okay.
Hello, Ligang.
Hi, nice to meet you, Binay.
Professor Rasuli, the stage with you.
Hello. Okay. Okay. Hello, everyone, and it is a great pleasure for us, and it's a great honor for us. We have Professor Wang as a keynote speaker of this conference. Actually, in this session, we will have 3 talks. The first one will be presented by Professor Wang. I should thank to Professor Pur Hassan for the file that introduced Professor Wang. And now we can start the presentation of Professor Wang. Professor Wang, you can start your talk and presentation.
Okay, and could you let me allowed to share the screen?
Yes, that work will be done by the office in Damgan. Maybe.
Right.
Yeah.
You can share now. You can share.
Yeah.
Okay. Okay. Now I will share my screen. Can you see the screen?
We have the screen, but not okay.
Yeah.
We have your.
I have 2 screens.
Your presentation. Yeah.
Yeah. Okay. Okay. So may I start my talk? Okay.
Yes.
Okay. Let's.
You can start.
yeah, let's start my talk. And it's the minimum. Okay. Good afternoon and hello everyone. And first, I would like thank the Dr. Benan's invitation, and also thank the organizer, Ligang University, and for organize this wonderful conference. And I'm sincerely wish this conference very successful. And I come from, I'm very happy to meet old friend and also the new friend in this chance, through this chance. And I come from School of Physics, Zhejiang University. And before my talk, I would like to thank my student and current student. And these students are evolve the experimental research. And my talk is about the structured light-based optical trapping and manipulation. And we design specific structural light field by using spatial light modulator, and use them to explore trapping and manipulating property of this kind of different kind of structural light. So let's here is my talk outline. And first, I would like introduce the optical tweezer and also about the structural light field. And then I will discuss our recent 3 works. And first one is we will realize the positioning and angular control of optical manipulation by using vortex-pair beams. And then we discuss the trapping and rotating features of fractional vortex beams. And last, I will present our very recent works on the trapping and transportation of the particles in the modulated Airy needle beams. And we know, and basic principle for the optical forces is actually related to the exchange of momentum of light. And when they interact with the matter or like particles, and due to the exchange of momentum between photon and particles, so the light force rises. And any change in the direction of light by reflection or reflection will result change of the momentum of light. So for ordinary light source, due to the high divergence of the light source and the low energy density, so the force on the macro object are very extremely small. But for a laser beam, due to the high energy density and highly directional beams, so the force on the macro-sized beam particles will be very significant. And so this force can effectively trapping and manipulate the macro-sized particle. In the history, and Peter Lebedjev was the first one to measure the pressure of light on a solid body in the 19th centuries. And his work was first quantitatively confirmed of the light force from the Maxwell theory of electromagnetism. But due to the lack of the high power density light source, the research on the optical force was very difficult before appearance of the laser. So until in 19 1960s. And after the invention of laser, it became possible to effectively focus the light and then generate the observable optical force. From 1960 to 80s, and there was a serious work done by Atkins group, and we know now, and people initially use the optical radiation pressure to manipulate objects like atoms and ions or bio cells. In 1960, and Ashkin and his colleague and reported first observation of what is now commonly used as optical tweezer, and a kind of tightly focused beam capable of stable chopping and manipulation in 3 dimensions on the macro-sized particle. And since then, and this area developed, and in 2018, we know Ashkin at the age of 1906 got the Nobel Prize. So after that, this area attracted a lot of groups and rapidly developed very rapidly. So here, this slide shows the basic for optical tweezer, and the key factor is the gradient force. And usually, for realizing 3-dimensional stable chopping, and we need both transverse and longitudinal condition to have the restoring force, and from the gradient force, and then the third one is we should overcome the Brown motion force, and also of course need to the force gradient force should be larger than the scattering force too. And this 3-dimensional force is very similar to the situation in the spring and restoring forces system. And from 1990s to the 21st centuries, and their research developed various optical tweezers like fiber optical tweezer, waveguide optical manipulation, also include the holographic optical tweezer and the surface plasma-based optical tweezer. And in recent years, we know and various new kinds of structural light can be generated due to the faster development of optical field control. And people start to precisely control the amplitude, phase, and polarization of the light field, and can generate through the novel engineering, and can generate many new applications and new freedom for optical technology. Here is a several example for various structured light like Ligang Gaussian beam and Besa beam and Airy Gaussian beam, and also like perfect vortex beam, vector beams. And this is an earlier example on the effect of vortex and spin on the chopped particle, and can make people to rotate the object, often a new freedom to control the macro-sized particle. And this is also very important in the optical macro machines and the biotechnology. And this shows that the different polarization can change the rotating frequency. And this is another example to show the spinning optical torque on the macro-sized object. And people to control the optical spinning torque, and that can rotate the calcite crystal sample. And as time being, you can see this crystal, the direction is orientation changes. And this slide shows a method to rotate macro object by using interference pattern of the vertex and the reference beams. And here shows a corkscrew like path on for the Poynting vector. So this will give rise an orbital angular momentum component. And here is the interference pattern of these two kind of beams. And so people can rotate the two trapped silicon sphere or glass rod, or also the bio cells like the Chinese hamster plasmid. And this slide shows the rotation of microparticle using the perfect vortex beam. And here you can see the rotating rate is proportional to the orbital angular momentum L. And here is the scattering of the certain trapped microparticle. So using the structural light is very effectively control the small particles. Here, and people use the base beams to trap and guide the particle along a line, and also can form particle chaining. And if we use a standing wave in the base beam, you can transport two particles parallelly. So here, and people even can use various Airy beams. This is your standard and Airy beam, and this is your circular Airy beam, and can manipulate and or guide or sort the various microparticles. So these are some very recent, excellent review article. If you are interested, especially for a young researcher, it's very good to know the whole area in the new development. And let's introduce our recent work, and we'll start from our text beam to manipulate and position in angular control of the optical manipulation. So vortex-pair beams and
again.
Okay. So vortex-pair beam, sometimes also called vortex dipole, and when these two vortexes have opposite topological charge. And people already started their focusing property, and even for electron vortex pairs. And here in our scheme, we propose to use the pure phase vortex pair beam. And such beam consists of two equal topological charge or two opposite topological charge. And for equal topological charges, and you can find two bright spots at the focal plane. And use these two bright spots, we can manipulate the two particle or macro-sized load. And since this is like an optical span, so when we can control the inter-vortex distance to adjust the distance of these two bright spots. This is our our setup, and we directly load the phase pattern in the spatial light modulator, and then send this generated vortex-pair into the microscope system and for the trapping light. And because the phase pattern is directly loaded in the SLM, so it's very simple to manipulate the macro-sized particle on the sample state. This is one of the results. You can see as decreasing the intervertex distance, and the trapped particle will decrease also controllably. If we rotate the phase distribution, and then you will find that particle will also rotate precisely. And here are some under the different laser power. We can see the control range are very stable under different laser power. And this picture shows the control range of the interparticle under different topology charge. And as the value of topology charge increase, the control range will increase too. So, and almost very linear. And we also use this kind of vortex pair beams with equal topology charge to manipulate a cylindrical like the microrods. And if we rotate the phase distribution evenly, and this will also rotate very evenly and very precisely. So these are detailed properties on how the rotating speed versus the modulating speed, and this downward due to the response limit of the spatial light modulator, because the frequency of the flash frequency of the spatial modulator is limited. So you can see the particle rotating speed is almost linear to the input power. This is a comparison of manipulation effect between the vortex pair with equal topology charge and the opposite topology charge. These are opposite situation. These are equal situation. So for the equal topology situation, you can see the rotating is very smooth and evenly. But for the opposite topology situation, and this is like very complex, but like a mopping floor. And so different trapping property due to the different focal property. And at the focal plane, for the equal situation, there are two bright spots, but for the opposite situation, the spot is curved. So, and here we also show the optical trapping force measured, and using to move the sample state. We measure this force in the x direction and y direction, and this show the maximum optical force. And also we can measure the trapping stiffness, and from the particle motion in the trap, and we can get the power spectrum, and then both in the x and y direction. So we can get the optical stiffness in both directions. And this trapping stiffness in two directions are very similar to the force, the maximum optical force. So this can be confirmed. Our trapping stiffness is reliable since it's matched to the maximum force. here are some similar for the chopping property of the vortex beams. I will not read them. And then we interest on another kind of structural light, that is a fractional vortex beam. And as we know, the vortex beam usually is with the integer topological charge. So there's a screw wavefront dislocation. But for the non-integer situation, and this phase front become a mixed screw edge dislocation. In the intensity profile, there's a dark gap in the intensity ring. So in previous research, people feel due to the existence of this dark gap, so the chopping property will not be very nice. But these are some research in the earlier times, in the 1990s. And when it appears for this kind of beam, and people are very interested due to their specific properties. And people research on the vortex strands. And we also researched on the vortex strands for the practical vortex beams. And we find a different law for the vortex strands, and also found at the focal plane, the intensity profile are very different from the ideal situation. So in the earlier times, there are some experimental to focusing on the chopping property of the fractional vortex beam. And this study actually showed the limited use of such beams because of the dark gap in the intensity ring. But we want to know, how about for the practical fractional vortex beam, since the focal property are very different from the ideal case. And here, this is our setup, and we load the phase fractional topological charge phase distribution on the spatial light modulated directly, and then move the sample stage below or up above the focal plane. And we will find when there are different chopping effect for when the sample stage displaced from the focal plane. At the focal plane, you will find if the particle, there are multi-particle, that the rotating is very smooth, but away from the focal plane, the chopping effect becomes worse. And for the less, particle number is less, of course, even for the fractional situation, the chopping rotating effect is not smooth. So we feel there are some interest chopping property for the collective effect for the multi-particle system. And here shows the chopping effect on the different fractional topological charge. And the video is slowed down by 10 times. And here you can see for 5 particles cases, and the rotating effect for practical fractional situation, and the rotating effect does not change too much. And so we interested the collective chopping effect for the multiple particle situation. And for less number of the particle, the chopping effect in the half integer of topological charge is really bad. And for the integer situation, it's better. And but for the multi-particle system, they are not have the big difference. So from the experimental video, we can get the trajectory evolution of each particle, and from then we can get the rotating period. So from the period, we can see as the particle number increase, and the rotating period will become step-like as the value of topological charge increase. So even for the non-integer case. Further, the rotating become faster and faster as the increase the incident power, and you can see the rotate become faster and faster. And we measured the collective orbital angular momentum for the fractional vortex beam, and as a topological charge increase. And these experimental data are very well matched with the cylindrical rate curve. And so we feel, we argue that this quantity as the square root of the product of the collective rotating period and the laser power, and can be reflected as orbital momentum of fractional vortex beam. And we also, from the motion of the particles, we get the power spectrum, and we can find the main rotating frequency, and to a shift as the topological charge changes, and also we can get the collective chopping stiffness, and there's a dip, not exactly at the half integer, but slightly larger than the half integer. Here, for example, it is 5.7, and because at this situation, and there's a dark gap in the ring, so the collective rotation will decrease. So the chopping stiffness will also decrease. And here is near 6.7, and it also has a dip. So we also use the fractional vortex beam to manipulate the biological yeast cells. And since yeast cells are considerable big size, so you can see all the operation, you can see they can rotate the cell smoothly. And so of course, for integer case, to move faster, but for half integer situation, or for fractional topological charge situation, the rotating speed will slow down. So these are some property for the fractional vortex beam, and there's a rotating, different rotating effect on the multiple microparticle at the different chopping plane. And if we away from focal plane, and the chopping effect will become worse. On the focal plane, and it will become rotating will very smooth, and also the collective rotating property will match with the fractional orbital angular momentum, and also we measured the collective chopping stiffness, and there's a dip at the slightly larger than half integers. And latest we consider to design a needle beam. So we use a circular Airy beam to modulate the amplitude of each rings, and this without modulation, the original circular Airy beam, and then we change the coefficient amplitude of each ring and use this expression. And of course, for the ideal case, there are infinite rings, but in our design, we use the finite number of rings, and it's not necessary to have the infinite. Actually, experimentally, use finite rings, number of rings will be much easier to realize, and also the quality to generate the needle beam are very high quality. And this is a process, and we use the first ring circle to cut the first ring, then modulate the amplitude, and also use the second ring to modulate the second ring, and so on. The third ring modulates the third ring, and sum them together, and also times the original circular Airy beams, and then we get the modulated circular Airy beams. And so this is the algorithm for generating the modulated circular Airy beam, and for generating the Airy needle beams. And here we consider an example for 3 links. And for 3 links, we have the 3 peaks in the longitudinal intensity distribution. Then we first adjust the coefficient A3 and make the middle peak smoothly, to smooth the middle peak. And then we decrease the A2, and then adjust the A3 again to smooth the middle peak again, and repeat this process until we smooth all the peaks in the longitudinal intensity distribution. And this table, and we present the in our experimental situation, get the for 2 links we only need 2 links to optimize A1 and A2, and actually A1 is always equal to 1, so we need only to optimize another coefficient for 2 link case, and for 3 link case, and we need to optimize and 2 coefficient. Of course, this kind of iterative process is very program consumed. So we use this algorithm to get the optimized parameter for generating the Airy needle beams. Here is our experimental setup for generating the Airy needle beam, and at the spatial light modulator, we use the complex amplitude modulation method, and this is an example for 2 links phase modulation, and this actually is a complex amplitude modulation to generate 2 links of circular Airy beam. And in 2 link cases, we can see after focusing, we can get the very uniform longitudinal intensity distribution, and the depth of focus in this case is nearly 319 millimeter, and the aspect ratio is more than 4,000. But for original circular Airy beam, the longitudinal intensity distribution is non-uniform. So you can see we really generated a very uniform longitudinal intensity distribution after such simple optimized 2 links. And also we optimize for 4 links and 5 links, and we can generate the needle beam with very high aspect ratio and very long depth of focus, and in different situations. Then we use such kind of beam in the optical chopping system. And this is a measurement for the longitudinal intensity distribution in the microscope system. And in this situation, we measured the depth of focus about 44 micrometers. Then we demonstrate here show the two examples in the weak flow fluid environment and the strong flow fluid environment. In the weak flow fluid situation, you will see, and the particle motion is very smooth, and the trajectory is very smooth, and so it's effectively to transport axially in the z direction, and in the strong flow fluid situation due to the opposite flow motion, so it can be stably equilibrium in the system. So you can see this particle is stable there, and also if there's another particle coming, then it will appear again. So you can see this is the second particle here, and because due to the opposite flow velocity, so it can stable there. And we also can use this kind of beam because it has a smaller blood spot for this Airy needle beam than the Gaussian beam. So we use the scanning confocal system to imagine the nanoparticle. And this nanoparticle is 100 nanometer diameter in diameter. So we can see using this Airy needle beam, and the imaging will better than using that Gaussian beam, and also is better than blood field imaging. So this is for the blood field imaging. This is using the scanning confocal system to get the imaging, and you can see this highlight place. And in the Gaussian situation, these two particles cannot be distinguished, but in the Airy needle situation, it can be distinguished clearly. And if the particle in density increase, we can see a clear difference for the Airy needle beam and the Gaussian beam. In the Gaussian situation, the particle, cell particle condense together in the imaging, but in using the Airy needle beam, we can distinguish them clearly. And here you can see we can distinguish them clearly, but in the illusion by the Gaussian beam, it's hard to be distinguished. In the blood field, of course, it was more. So this is our summary of 3 works, and we first work using the vortex-pair beams, and in this system we precisely demonstrate the 2-dimension optical chopping and the rotating operation. Just and also measured their stiffness. And in the second work, we consider the fractional vortex beam and to explore their optical chopping and rotating effect in the collective situation or multi-particle system. And we find the collective chopping stiffness has a dips at the slightly larger than the half integers, not exactly at the half integer. And the latest one, we show the designed Airy needle beam really can have the axial transportation of the macro-sized particle, and also can use for the high resolution imaging than the Gaussian beam. Okay, thank you.
Thank you very much, Professor Wang. Thank you for your very clear and helpful presentation. Actually, I'm very, very interested to your very nice works and very deep works. And I hope all of the participants enjoyed, like me, with your presentation. Very useful presentation. Actually, we have time to have some question. If anybody have a question, let me know, then I can turn on the microphone, and personally you can ask your questions. Also, you can use the chat box, then I can read your questions, if any question. Actually, Professor Wang, I have a question. In the trapping of the particles, especially when we ask to trap multi-particles, we need to generate multi-beams. And the big challenge in this generation of multi-beams is the efficiency of the beam. What part of the incident beam can be inverted to the beams used for trapping of multi-particles? Can you say about the efficiency of the energy transfer to the desired vortex?
Okay, thank you for the last question. Yeah, in our system, we actually still use a single beam, and you can see this vertex-pair. Actually, the host beam is a Gaussian beam, only single one, and not for the. But as it propagated, because its focal property can form two focal spot, so it's due to its earn property, not we generate two beams. So actually, initially we only have a single Gaussian beam, and but in the experimentally for the efficiency, mostly it's limited by the spatial light modulator, and if the spatial modulator deflection efficiency is low, then the energy transfer from the original laser to the trapping laser, and then it will become low. So it's limited by the, but here we do not use the holographic method. We just select the phase distribution. So this efficiency is considerably high, reach to the near to the 60 or 70% energy from the original laser beam, and because these are not used directly load the phase, so efficiency will much higher. But for generate and also for the fractional vortex beam, when in our system, this also directly load the phase distribution, so efficiency is much higher. But for the last one, efficiency is low because we use complex amplitude modulation. So the efficiency for this system in the spatial light modulator, I know Professor Lasoli also do the structural light, and so if you use the complex amplitude modulation, the efficiency will become low. So for this one maybe only 2% energy from the initial light. So it's well limited, but it's sufficient for us if the initial light has 100 milliwatt, and here we can have the tens of milliwatt. So it's still sufficient for manipulating the microparticles. But for the multi beams, if you generate multi beams, then it will requirement for the original laser power maybe needed to the several hundred milliwatt. Then maybe each, for example, if you generate the optical array, then each beam, because if you want to each beam to manipulate the particle, then each beam there are minimum power requirement. Yeah. Okay. Thank you for the last question.
You are muted, Professor Rasuli.
Oh,